Welcome to Explore Embedded. This is a new tutorial series on ARM, and I should really thank you for watching the 8051 and the AVR series, and a whole lot of good comments that encourage me to do more of these tutorials. So now I'm bringing you a whole new series on ARM microcontrollers. Now, so before going ahead, I would like to give you an overview of what we'll be covering in this series and in this video in particular. So first, the series. So we'll start with the basics of ARM microcontroller, Cortex microcontrollers, how to program them in C, and how to write simple applications or simple C code to control various peripherals like the LCD, micro SD card, Ethernet, and all of that. And in the second part of the series, we would look at porting a real-time operating system on the Cortex microcontroller that we'll be working throughout in the series. So that is overview of the series. Now in this particular video, we'll be looking at simple basics as to there are various families of ARM microprocessors or controllers, as you should be knowing, and so we'll be looking at this in this tutorial at what are those various families and where does Cortex M series stands and why we are using it in this series. We'd also then go ahead and look at the block diagram, so of how a controller is made from a Cortex processor. So what I mean by that is what ARM as a company gives is just the IP of the processor, and there are various other vendor companies who come up with controller designs and they make a controller out of that core. Now, so we'll be looking at a generic block diagram of what that is. And after that, we'll be in this tutorial series, we'll be using the LPC1768. So we'll be looking at the features of that particular controller. And once we do that, we'll move ahead and look at the programmer's model and the resistors inside the microcontroller. But before we go ahead, let me just clear one thing. So you need not know all the architecture details to get started and write programs for the microcontroller. So we'll be doing exactly the same. We'll not be going into the details of what resistors need to be configured and all of that right now. So we'll be going ahead and looking at it from a programmer's perspective as to how you take a controller and write applications for it. So let's just go get started and get going. So let us look at the various ARM controllers that are there. And in fact, I had attended a conference last year, the ARM Symposium, and they have got such a range of ARM-based microcontrollers that there are different versions, there are different naming conventions that it is literally impossible to comprehend all of that. But to keep things simple, this is what you can remember. So the Cortex A series of microcontrollers or processors, these are application processors. So what I mean by that is you should have seen a whole lot of smartphones, tablets, they too use ARM based controllers, and even a closer example is the Raspberry Pi. So it runs a full-blown Linux. So all these application processors, they run an entire operating system. So these are the Cortex A series of controllers. Then next to that, and this, as you could guess, these run in gigahertz, they have a lot of flash and RAM and all of that stuff. So these are all application processors. So for a comparison, you could say Raspberry Pi falls in this category. So it has a controller which supports porting of an operating system on it. The next in line we have is Cortex R series. So R, it stands for real-time operating system. So these are specific processors on which you have an operating system running. For example, it could be your automotive applications like a car, wherein you will have various nodes and operating system running on the center, and then various processes communicate in between, and you'll have a real-time OS running over there. So those are Cortex R series processors. Okay, so this, you can say an apt example would be automotive. Then we have the Cortex M series, and this is a typical microcontroller. So this has features which are greater than, say, 80 mega 328 that is used on Arduino, and it is less than the application processors or the real-time processors. So typically these are the controllers that you would use in a lot of your applications. So you could have come across the limitations of AVR 80 mega 80 mega 328, wherein we have very few features, limited code size, that is limited flash, limited RAM, a limited number of IO ports, and all of that. And that is where you try and think of switching it to a higher processor or a higher microcontroller. And so in this tutorial series, we'll be looking at a particular Cortex M3 series of M3 series controller, which is LPC1768. So in a little while we'll look at what features it has and all of that. So you could, following this tutorial series, you could even use any of the other Cortex M series microcontrollers. So this is the microcontroller series. So these are widely used in a lot of generic applications where a microcontroller is used. And then they also have something called a secure core, which is used in security applications like the SIM cards and all of that, which will not be seeing in this series. So let's just go ahead and see at a block diagram as to what a typical microcontroller based on ARM core looks like. So what you have in the first place is the ARM processor itself. So this is the core processor, and this is what is provided by ARM as a company, and all the rest of the stuff that you see on this block, it's done by the microcontroller manufacturer, who puts in all the various systems and make a controller work. Now, so to get started, let's look at the memory part of it. So typically you will have a flash memory on a microcontroller, which is where you store your code in. So when you write a C application, all the program code goes into flash, and whatever program data that you have, it goes into the RAM. So typically you will have a flash programmer interface to write this flash memory. And then apart from that, you will have various other internal features, or in a controller, typically like Ethernet, UART, SPI, TWI. So all these are serial communication protocols, so you should be familiar with this. And then there is a Ethernet, so we'll look at this shortly. You will have the Ethernet module inbuilt, so that you can connect the controller to the internet. And then you have inbuilt CAN. CAN is a protocol which is used in automobiles, and in most of the automobile applications. And then you have USB, the all familiar serial interface, which you have in your laptop, so you can have that on the controller as well. Then there is PWM, which is used to control motors, drives, and all of that. So, and you also have some timers and counters. So let us go ahead and look at the specific features of the controller we'll be using. So the controller we'll be using in this series is LPC1768. So this is Cortex M3 based 32-bit controller, and a major shift from what if you have worked with controllers before is this is a complete 32-bit controller. So the difference is, like, if you have seen libraries like Ethernet and the TCP/IP and the SD card and all of that, they take a whole lot of code, and these are all written for 32-bit applications. You can port them directly on a 32-bit processor. So that's one advantage, and it runs at a very good speed. So this runs at 100 megahertz compared to your 16 megahertz of Arduino. So it is in between your Arduino and the Raspberry Pi. So and then it has 512 kilobytes of flash. So this is the memory that is used when as I said before, so when you write a C code, and the code it gets compiled and it is stored in the flash. It also has a RAM of 64 kilobytes. Then there are USB ports which can act as a device and host. So we'll look at that a little later. It also supports CAN. Then while interfacing, you could have come across this. So you just have a couple of UARTs, and then on a Arduino, and then you do not know what to do. I mean, the basic Uno. So you use a soft UART. So instead of that, if you look at this particular controller, it has 4 dedicated hardware UARTs, and one of them has full modem interface. That is, it has additional signals like the DTR, RTS, and all of that. And it also supports 3 I2C, or the wire, the wire library. In Arduino, it supports 3 such I2C protocols, and there is also SPI support. So we'll look at all of these later. Just to give you a hint, SPI is used to interface a whole lot of displays, memories, and all of that. It also features a 12-bit ADC, a 10-bit DAC, and 1000 Ethernet, which is a decent speed for a microcontroller. And then you have 4 32-bit timers. And then the controller has a nested vector interrupt controller, which handles all of the controller interrupts in a very good way. So we'll look at that later. So apart from that, you'll have a whole lot of GPIOs on this controller. So this is a 100-pin controller we'll be working out throughout this series. So let us go ahead a little ahead and look at the the programmer's model. Now this you need not know at this point in time, but just to show you the capabilities of how controller runs, I'll be showing you what a programmer model is, what are the states the controller works in, what are the modes, and the access levels. So let us look at that in a quick way. So it works in 2 modes. So the 2 modes are it's called the handler mode and the thread mode. So now thread is the instruction set that the the Cortex M3 works on, and there are 2 modes. So the thread mode is when it is executing those instructions. It is the normal instructions is the thread mode, and whenever an interrupt occurs or whenever a routine is called, it goes into the handler mode. So basically the controller can work in either of 2 modes. It could be thread or it could be handler. Then again, there are 2 states in which it works. So the first is thumb state, that is when it is executing normal instructions, and the other is debug state. So in the modes I said thread and explained what you mean by thumb. So basically the mode is simple. Let me just tell this once again. So handler is when your interrupts occur, and thread is the normal execution of the program. So basically all the while the controller will be going or running in thread mode, and then whenever an interrupt occurs, it goes to the handler mode. So coming back to the states, so there are 2 states. There is a thumb state which is normal execution of instructions, and there's a debug state wherein you can debug the processor. And then there are two access levels. One is the privileged access level and the other is unprivileged access level. So let's just go ahead and see how it switches between all these states. So whenever a controller boots up, it runs in the thread mode. So you have it running in the thread mode, and the access level here, it's I'll write it P for privileged, so that in this mode, when it starts, it has access to all the peripherals, all the memory and everything that you want. So this is in privileged mode. Now whenever an exception occurs, like say whenever an interrupt occurs, it moves from the thread mode, to the handler mode. So this is your handler mode. So basically it is, if you come across the other controllers or processes, this would be as good as running an interrupt service routine. So it switches from thread to handler whenever an exception occurs. So, and it could come back, and there is, again I said, there is a privileged mode for all of this and an unprivileged mode. So say there is an application where you do not want to give access to the entire controller, so you can make the controller work in two modes. So one would be privileged and other would be unprivileged. So let me write U for it, and then you can switch between this privileged mode to unprivileged mode with the help of software. So you can modify some registers and you can switch to that mode. So again, when it is working here, it is again in thread mode. So thread mode from an unprivileged access level could also generate an exception, and that again goes back to handler. Now from handler, depending on what code it is running, it could get back to the thread mode, which is privileged, or it could go back to the thread mode, which is unprivileged. So basically, to just to wrap it up, so what I would suggest doing is just understand this particular basic concept. So it runs in thread mode all the while. Thread mode is the normal application code, and whenever an exception occurs, it jumps to the handler mode. And you could make the applications run under privileged state or unprivileged state in the thread mode. So normally while writing C programs, you would not have to worry much about this. And all this this state where it is running, it's called as I said before, so this entire thing is called the thumb state. And now there is one more state called the debug state. Now so debug state is when you want to execute one instruction at a time. In that case, the processor goes into the debug mode. So it starts in the thread mode with privileged access, and then if a JTAG connector is connected to the development board you have, and if you make a request to debug the processor, it goes to the debug mode. So this is the debug state, and it could return back from the debug state when you release it from the debug state. So the importance of debug state is you can actually go inside processor and you can execute the instructions step by step and see what is going wrong. So this is pretty handy when you want to debug various applications and code that you write. So before we wrap it up, I'll quickly show you the registers that are there in a normal Cortex M3 processor. So the register set, it's pretty if you looked at other processors, these are very limited number of registers, but still it works extremely well. So you have 16 basic registers, and they're divided into two groups. So the first 8 are the low resistors, and then next 6 are the high resistors, and there are 3 special resistors that you see here. So what you see here is this R13. It also, the R0 to R15 are all general purpose resistors, but these 3 have additional special function, and the R13 is the stack pointer. Now there are 2 stack pointers. We'll discuss all of this later. So basically this handles when an interrupt occurs, the stack pointer handles how the control switches between the the execution of the interrupt service routine and the main code. So that is done by the with the help of stack pointer. Then there is a link resistor. So the link resistor, it's basically, whenever the controller goes into interrupt service routine, this link resistor holds the address of the, holds the return address. So after executing the interrupt service routine, the controller reads the link resistor, and determines at what location it should come back and start executing the normal program. And program counter, as you know, with all controllers, it keeps pointing to the next instruction in the in your program. So basically you have three resistors, 3 special resistors. So the stack pointer, it handles pushing and popping of the data to the stack. Link resistor, it returns holds the return address whenever the controller goes into an inter-service routine. And then there is a program counter which keeps pointing to the next instruction to be executed. Apart from that, there are special function resistors which tell you at a point in time what is the status of the processor itself, as to what mode it is in, or what it is executing. So this will not have to worry in the first part of the series, because we'll be interfacing all of the peripherals and we'll be writing a code in C. So we'll not touch assembly in this particular series in the first half. So so these are all the basics that I wanted to cover before we go ahead and write our first simple C application. Now to in the next video we'll see how we can set up the tool chain. So there are various tool chains that you could use. We'll possibly be setting up the co-IDE with GCC or code blocks with GCC. So these are open source and free tool chains that you could use. There are other options as well, like the Keel and the like. So before I end, I would like to also show you something else. I would like to take you to GitHub, and then I would like to show you the code libraries that we have been building for quite some time now. So GitHub, if you go to Explore Embedded, and then if you scroll down to code libraries, so we are trying to build C libraries with no overhead, and libraries which you would use for all of these controllers: 8051, AVR, PIC, and ARM. So right now what you see in the repository is 8051, AVR, and PIC. So we'll also be adding ARM as we go along with this tutorial series. So what you could find in all of these tutorials is all of the peripherals that you have on a controller, you will have consistent function names, so that whenever you switch a processor, you need not have to worry about your code libraries. So these are all the libraries. So just to give you an example, like say ADC, for instance, all the controllers would have a ADC initialization function and a ADC get value function, which would return the analog value. So it would be consistent throughout throughout the controllers and processors. Now if you feel these are important and you would like to contribute, download, test the libraries, give us feedback, write patch to it, you could fork it, and you can submit the revisions. So this was a quick announcement, and there's one more thing that I would like to tell you, that this tutorial series is brought to you by quite a few people in Explore Embedded. It's not me alone doing the tutorials here. There's a bunch of team. So next time when you thank or subscribe, say thanks to everyone around here. And we look forward to your comments.